All right, we're at section 9.3. This is an analysis model of non-isolated systems. Momentum is what we're studying. And so let's look here. We've already studied the fact that the sum of the forces is equal to the time rate of change of momentum. This is the way Isaac Newton expressed it, as opposed to force equals mass times acceleration. So the sum of the forces equals to the time rate of change of momentum. So if we can see that dp is equal to the sum of the forces to dt. And so we see that the change in momentum, delta p, change in momentum, p final minus p initial, is equal to the integral of from initial time to final time of the sum of f dt. And so we're going to find out that it's this is something that we call impulse. A force over a period of time is an impulse, and that impulse causes a change in momentum. It is the impulse that causes a change in momentum. Now here is an impulse. The impulse imparted to the particle by the force of the area under the curve. That is the impulse from Ti to T final. You can imagine a fastball approaching a batter, and as he hits the batter, as the batter hits the ball, when the first makes contact at T initial, it's just a little bit of force. As the batter continues his string, it maximizes the force, and as it leaves the bat, it diminishes again, and you see an impulse waveform, sort of what's shown in A. Well, you can get a time average of the net force, and it gives the same impulse to a particle as does the time varying force in A. So in A, we have a time varying force. In B, we have a time average net force, and it'll give the same impulse. Okay, so the sum of the forces average is defined as 1 over delta t, the integral of the sum of f dt. So we'll see that the impulse is equal to the sum of the average forces times the delta t times some time interval. Now that, so we have F average is equal to the sum of the forces, where force is assumed to be a constant. Now, impulse is the sum of the forces times a delta t. Some force times delta t is a constant net force. It gives a constant net force at a particular time. That's impulse. The change in momentum of a particle is equal to the impulse of the net force acting on the particle. Delta P, change in momentum, is equal to the impulse. It is the impulse that causes a change in momentum. Now, why is this important? Why are they showing you a picture of a crash dummy? Because this is an application of impulse and the change in momentum. If you let's look at this equation. Well, let's see. Let's look at that bottom equation. You have an impulse, a change in momentum. You can imagine a mass going. The change in momentum is a mass times the final velocity minus initial velocity. That's a delta momentum. So if you're going 100 miles an hour and you come to a stop suddenly, well, if you come to a stop, that's like mv final, that you're 100 miles an hour. Well, I don't know what it is in meters per second, but it's pretty fast, and you go to 0. That's a change in momentum. Now, the time it takes to change that momentum can be life-saving, and we'll see what we mean. Um, if you can imagine, uh, I don't want to imagine a person. We'll just stick with the crash dummy here. Uh, but the crash dummy without a seatbelt, without airbags, if he's going, even if he's going, 60 miles an hour and hits a wall, his momentum is changing. Delta M, delta V. So the his mass times uh, final velocity minus initial velocity is going to equal to force times time. It's an impulse. Now, if he strikes it very fast, if there's no seatbelt, if there's no airbag, that delta T is pretty small. It's in milliseconds. So that's a large force. If we divide that delta P by delta T, we get a large force. Now, what if you can increase? Whenever you can increase a denominator, you're gonna increase the denominator, you're gonna decrease the result. So if we can lengthen delta T, we're gonna reduce the force. So we put a seat belt. That changes. His car is still gonna come to a stop, but they do have what are called crumple zones that cause the car, instead of back in the days when they used to make these heavy steel frame cars, and there wouldn't be much there wouldn't be much crumple. You would hit and you'd suddenly stop. Now they have crumple zones that absorb some of it, but that's getting off the subject of this picture here. So we put a seat belt, and now you've lengthened the time that the crash dummy comes to a stop. So you've increased the delta T, you've decreased the force. Now you put an airbag in combination with the seat belt. You've increased the delta T a little bit more, so you decrease the force. Here's another example. You see, you're on the highway and you see the exit ramp. What do you see in front of the concrete barrier that separates the highway from the exit ramp? You see these barrels of sand, there to absorb the crash, there to increase the delta T. You increase the delta T, you have increased likelihood of surviving the crash. That's why you see those yellow barrels. It's to slow things down. Okay, so there's some examples. Delta P, the change in momentum, is equal to impulse, is equal to delta F. The sum, I said delta, sum of the F average times delta T. Impulse approximation, I'm talking too fast. Assume one of the forces exerted on a particle acts for a short time, but is much greater than any other force present. Okay, so using that force, if you can increase the time, you can decrease the force. Okay, here's some quick quizzes. Two objects are at rest on a frictionless surface. Object one has a greater mass than object two. Let me catch up on my notes. Object one has a greater mass than object two. So M1 is larger than M2. When a constant force is applied to object one, it accelerates through a distance d in a straight line. The force is removed from object one and is applied to object two. At the moment when object two has accelerated through the same distance d, which statements are true? There's, on the top line are the momentum statements. Momentum one is less than momentum two. Momentum one is equal to momentum two, and momentum one is greater than momentum two. And then in the bottom, we have the kinetic energy considerations. K1 is less than K2. K1 is equal to K2 or K1 is greater than K2? Well, it's going to be C and E. We're going to the momentum of the P1 is greater than P2, but the kinetic energies are equal. So object 2 has the greater acceleration because of its smaller mass. Remember, we said that object 1 has a greater mass than object 2. Therefore, it travels a distance d in a shorter time interval. So even though the force applied to object 1 and 2 is the same, the change in momentum is less for object 2 because delta t is smaller. The work equals force times distance. Well, they both go this. It's the same force. That's what it says. When a constant force is applied, and they both go the same distance. So force times distance equals a change in kinetic energy. So the work done on both force times distance is the same. So the K1 equals the K2. Okay, now we have another. Two objects are at rest on a frictionless surface. Object 1 has a greater mass than object 2. When a force is applied to object 1, it accelerates for a time interval of delta t. Now the force is removed from object 1 and is applied to object 2 for the same time interval. So the force times the delta t is the same. What does that mean? That means the impulse is the same for both. So which statement is the true? Which statements are true? Upper line is for momentum, lower line is for kinetic energy. The impulse is the same in each. Impulse causes a change in momentum. Well, so the impulse causes a change in momentum. So the change in momentum is going to be the same. So P1 is going to equal P2, but the kinetic energy for 1 is less. So got to catch up. The same impulse is applied to both, so P1 is equal to P2, but object 2 has a larger acceleration due to its smaller mass. Therefore, the distance the object 2 covers in the time interval is larger than for object 1. So as a result, more work is done for object 2, and so that means that K2 is greater than K1, which gives us D that K1 is less than K2. Okay, an automobile dashboard, seat belt, and airbag are each used alone in separate collisions from the same speed. In terms of impulse, rank these from greatest to least. In terms of impulse, and they're all going to be the same, because they're all going to cause a change in momentum. They're all going to cause there's going to be a delta p, which is from your initial velocity to a final velocity, usually of 0. So the impulses are all of them are the same. Now, in terms of the average force each delivers to a front seat passenger, rank these from greatest to least. And it's probably the greatest is the dashboard. Back in the day when I was a kid, dashboards were metal. Then they started putting foam pad on them, exactly for that reason of increasing the delta T. So, but from greatest to least, the dashboard is the greatest, then the seatbelt, then the airbag. Each one of those has a larger delta T. The larger the delta T, the lower the force. So you can see here in the first case with an isolated system, there was nothing crossing the system boundary. So the change in the total, here we do have an impulse crossing the boundary. So the change in the total momentum of the system is equal to the total impulse on the system. And this is, some examples are a baseball striking a bat, a spool sitting on a table pulled by a string, a gas molecule strikes the wall of a container holding the gas, and photons strike an absorbing surface and exert pressure on the surface. All of those are examples of impulse. Okay, and now we're gonna stop here and we're gonna talk about collisions.